Today we're going to talk about 3D printing materials, why you might want to use one over the other, but mostly focused on different transition temperatures. Hello everyone, Chris here. The topic of 3D printing material is one that you can go down a rabbit hole really quickly. Now recently I've been working on projects that have 3D printed materials outside in the summer heat, and that can pose a lot of challenges when you're working with plastics. We do have a lot of options with these hobby-based 3D printers on materials we can use to help combat that, but some of them come with their own challenges, and that's what I want to talk about today. I'm going to do my best here to try to stay on topic, not get off onto things that don't really matter, but there is a lot to this. Anywhere from measuring that part, designing it in CAD to have those tolerances for those different types of filament, as well as printing it accurately and the material that you're going to use. So bear with me. Let's start by taking a look at the part that I created that's going to be the subject for this video today. So you will have to use your imagination just a little bit, but what this is a clip that you can snap on to a baluster. This is just a section of the baluster I didn't use for my deck. This will clip on the baluster, and then this barrel will set in an eyelet to hold down a curtain. A pretty simple part, but in the summer heat, this can be pretty difficult to design and use. But to get the gist of this, you have one side of the hook, the barrel portion that holds the curtain down, it just slides into this part, and it has to fit around the baluster pretty tight so that you can slide it down to hold the curtain in position. So it's just a friction fit. It has to move some, but it does have to be pretty tight around that part to be helpful. So it's a very simple part that's easy to create that serves a purpose. When I create any project like this, I start with PLA filament. It's very easy to print. All of my printers can print it, and it's very affordable. And just a little bit easier on the environment because it is corn-based. But those specs for PLA, they're going to be pretty close to what you design in your CAD program. You'll see more of that. So then we go to designing the part. So here's the part in Fusion 360. And this is all important because we're going to get to different materials that don't act the same way as PLA does. But we're just going to make sure that the dimensions of the part are accurate after it's been printed out. So we'll just do some inspecting here. From this wall to this wall in this clip, we're going to work on this clip, not the round side, the flat side, because it's easier to measure. It's 3.2 millimeters. Also, if we take into account how thick this wall is, we're at 2.171 millimeters. This is a great way to tell how accurate the part is. So keep these measurements in mind as we start talking about this part more. The baluster is right at 32 millimeters square. I put in the 0.2 to give it some tolerance so that I was sure that it would fit. Again, these do have to be pretty tight or they wouldn't be that useful. So now we're starting to collect all the bits and pieces to solve this problem. I need a clip that holds the curtain in place, I need to go print it on my printer, and I need it to be functional. And we've already got it spec'd out in CAD, so we know exactly what we need to do. So you print it out in PLA. And that's exactly what this clip is that I just showed you before. It serves the purpose. You put it on the side of the baluster here, you slide the retaining section, that flat section on, they meet, it holds on really snug, it serves the purpose. And if we were to measure this clip, now that it's in the real world, we'll take our calipers. Remember, I told you that side wall is going to be a good indication of how big this part is if it's the same size as it is in CAD as it is in the real world. There's a lot of rules to measuring things. The first one that I can tell you to always be sure of is don't measure the side that's been on the build plate. I know this is the top surface just from looking at different parts over the years. I printed this on a smooth sheet. The bottom is smooth. No matter how accurate your first layer is, you're probably going to have just a bit of squish that's going to be wider than the rest of the part. So avoid getting your calipers on that first layer. So we'll just go from the top, we'll grab a section of it here, and we are at 2.15. In CAD, it said 2.17. That is close enough. Now, that's an easy measurement to give with calipers. Remember, we measured in CAD from this edge to this edge. You can do that, but you have to be careful. And here's the part where I go just a little bit overboard on how to use calipers to make sure that they're accurate. I think a lot of people struggle with this, but this is what I do to ensure that my caliper measurements are as accurate as I can get them. So what I want to do with the calipers is measure from this side to this side. Remember, avoid that first layer. So we'll put that first layer up so that I can put the arms of my caliper inside here, and then I can take a measurement. But you notice that part is skewed. Well, that's going to skew your measurement. And on a set of calipers, they overlap one another. You can see that this arm is on top of that arm. So to get an accurate reading, you really need to know what that gap is so that your part, whatever you're measuring, is parallel to those arms. Now, I'm using just a very affordable set of calipers off of Amazon, but I know the dimensions of some of these parts so I can more accurately measure things. But we'll take another set of calipers just to give you an idea of what's going on here. Always make sure your calipers are zeroed. But I'm going to measure this arm. That arm is roughly 2 millimeters and 70 micron. So close enough to 2 millimeters that we can call it that for these purposes. So this is a 2 millimeter rod. It is accurate, dead on 2 millimeters. So what I do is I'll take the part that I'm measuring, and remember, we have that arm back there. It's 2 millimeters thick. I'm going to put that towards the part and open up the jaws. The jaws, on a flat spot like this, the jaws will make sure that it's fairly accurate up and down. You can be pretty sure that the bottom of this part is parallel with the caliper because it is flat in the jaw. So no worries there. The part that's hard to compensate for is that skew there. But now that we know that back arm is 2 millimeters thick, roughly, I'm going to take my 2 millimeter rod and put it under the other arm. That way, I know that both of those arms on the caliper are parallel with that part, and they'll be accurate. And you can see the measurement is at 32.11. We were at 32.2 inside Fusion. That's a measurement that I would expect from PLA filament. It's fairly close. So we're getting closer to the root of this video. We're going to basically talk about using plastics in high heat environments where they could deform, PLA being on the lower scale. But now we have a way to measure the part that's consistent, and we know our starting point. In CAD, we requested a certain amount, we printed it out in PLA. It's fairly close. It's a little bit smaller because there's always going to be some shrinkage with these different plastics, but it's going to be a lot more as we move into the higher temp materials. And you have to compensate for that. So now we'll build on top of that. So we've got our PLA clip. We know it serves the purpose, it fits, everything looks good, and it's pretty close to what we requested the printer do via CAD. Now, this is going to melt at around 60 C. That's the transition temperature. That is not hard to do on a summer day in the Midwest. So this is going to be pretty much useless to us, holding that curtain down day after day. We're not going to be able to use PLA. Again, it is by far the easiest filament to print. But next up would be PETG. It's the same clip. I just printed it out in PETG filament. Now it's going to get you to 80 C. So it's going to be able to handle a lot more tasks than PLA would, and it's almost as easy to print. But even being just a little bit higher temp filament, you are going to experience more shrinkage after it's printed, after it's been cooled down. And that's what we're talking about here, trying to compensate for that. As you start moving up into the higher temp filaments, it's going to become more of a problem. So to continue gathering data for our experiment, we'll move on to measuring this PETG clip. We're going to line it up the same way we did the PLA part, avoiding that first layer. And we'll use our rod to compensate for the width of that arm. And we're setting right at 32.05. You can already see just a little bit higher temp filament. This part did shrink a bit. Now, it's less than 100 micron. You're probably not going to see any difference, but it is there. It is a different shape. Now, does this part still meet our needs? Of course. That's not enough to cause us any issues. It clips together. It's not any tighter than that PLA part. It would work just fine. So the lesson to take away from that is when you're printing in PLA and then you move to PETG to get just a little bit higher temp tolerance, you're probably not going to struggle with accuracy issues at all. They're going to be fairly similar. It doesn't shrink that much after you've printed it. Now, probably moisture is going to be a bigger issue than actually the different temperature range for PETG, but that's a completely different story. It's also a great time to mention, we're not even talking about 3D printer accuracy here. I am assuming that your machine is already very accurate. You can obtain these types of dimensions that we're talking about here, as well as your filament. It has to be accurate as well, or you're not going to be able to dial these in to be able to measure them correctly. So all that has to be taken care of before we do something like this. But again, we're making assumptions. So now with PETG, it's fairly accurate, the part works, but it's still not tolerant enough for the kind of temperatures that we see out in the backyard. So we have to move to something else. So to recap, we've got PLA, around 60 C transition temperature. That's the temperature before it starts to deform and move around. We have our PETG, that's around 80. The next logical choice would be ABS, which I don't use, but you do have ASA. The reason I don't use ABS is because ASA has the same qualities and it's much easier to print. So to continue gathering data, we're going to take our ASA print. Remember, it's the same exact STL file. We're at about 31.9394. So it shrunk even more than the PETG did. Now, is it still functional? Probably so. We'll go ahead and try it. It is noticeably tighter. And if you take a look at it, you can see how the baluster is actually bowing that clip out because it is tighter. If you compare that to the PLA one, you'll notice that it isn't getting deflected as much as the ASA one is. So the ASA clip has definitely shrunk a bit. It's a bit tighter. But ASA is going to have around 100 C transition temperature. And that is probably more than enough to withstand any temperature that we might see outside. So probably still a good choice. So ASA is going to fit the needs that I have for this part. Now, it would be nice if we could adjust it a little bit. We'll talk about that more in a moment. But there are higher temp materials that you can use. And the one that I would see at the end of the hobby spectrum would be something like polycarbonate. Now, you can always kind of use it as a rule. The bed temperature that you print at, that's probably around the transition temperature, because the purpose of that bed is to keep the filament somewhat soft so that it sticks onto the bed. And you can use that rule up to a certain point. Now, ASA, probably around 100 C. And similar materials around ASA, like ABS, it's going to be the same way. But when you get to polycarbonate, it would actually be closer to around 150 C. And most of the time we print it at around 110 bed temperature. So it's not going to be one for one, but you can usually kind of follow that as a guide. But let's take a look at polycarbonate real quick. So again, building on our example, PLA 60 C, PETG 80 C, ASA around 100 C, and then we have polycarbonate. Depending on the material, depending on the filament brand, what they've mixed it with, you should be able to see 150 C on polycarb. And for this measurement, the shrinkage that you see is roughly the same as ASA. But also take into account, we're just making one measurement. If you are seeing shrinkage on a part like this, the whole thing is going to shrink. And based on thermal mass, it might not shrink uniformly. So no matter how you measure the part, until the moment you get it to function how you expect it to in your scenario, you're really not going to know how it's going to react. So if we try it as intended, the clip is just way too tight. If you really press, you can get one in there, but the other one is never going to line up. So there is considerable shrinkage when moving to polycarbonate. But I have to tell you, polycarbonate is super impressive. It can be very tricky to print, but when you get it right, it's almost unbreakable. So part of what I'm trying to say in this video, based on the part that you're printing and the material, they're not all going to be the same. You're not going to be able to predict how that filament's going to react. If it is prone to shrinkage, like ASA or polycarbonate, based on the amount of material you use, even how you situated it on the bed, there's going to be differences from different dimensions to different dimensions, different size parts. Now, if you have the same part that you print over and over, or you're trying to just get a little bit higher transition temperature, like we're doing here in these tests, you should be able to somewhat predict how that part's going to shrink as you move up through the different thermal levels, like we did here, PETG, ASA, all the way to polycarbonate. And you can compensate for this shrinkage in your slicer. So back to thinking about how we design things. I designed this in Fusion 360. I don't want to mess with these dimensions. I know that if I printed it out in PLA, it would fit my needs. So I'm okay with the specs of the part. Now I just have to deal with the nuance of the filament. That's best left to the slicer. So say we wanted to try to combat some of that shrinkage that ASA gave us. You saw that it was slightly bowed when we tried to use it on our baluster. It still fit, but it'd be nice if it was just a little bit bigger. It's going to be very hard to do any measurements that make sense on that part to know how to scale it. And that's exactly what we would do. So for this part, we're not concerned about Z. The height really doesn't matter in this application, so there's no need to try to scale that aspect. So you can unlock and just scale X and Y. And I highly recommend, if you're going to try to do this, do X and Y equally. That way, anything that you have here, like these clasps, will still fit after these get printed out. So everything will grow, not just one aspect of it. So you can see real world size, 5587, 6557. Let's say we go to 101 and 101. Now we're at 5643 and 6622. So you can see just how 1% of scale will interact with the actual size, the real world size of that part. And most of the time, to compensate for the different levels of thermal filament and the shrinkage, this is exactly the kind of thing that I would try to dial in. So back to the real world, let's just take a section of our clip here. So our PLA clip, 3664. And we're going to do our best to measure our ASA clip exactly the same way. ASA, 3654. So we have about 100 micron to play with here. So we'll reload our parts. And let's just see what Prusa Slicer says about the dimensions on these parts. The same one that we just measured. We'll measure from this face to this face. 36.7. So PLA was 3664, ASA was 3654. So I need 100 micron across there. So we should be able to add that in our real world size, our scaling factor over here. So we're just going to take 53.6 and make it 4.6, and 42.92, we'll make it 43.02. And if we measure again, Prusa Slicer now says that's 36.777. And remember, we're scaling the whole object. So that gets us pretty close to that 100 micron we need. It should be a better fit when we print it in ASA. And you can take that same scaling and apply it to the other part, because you'll have to make them meet up. So we did 100.21 scale factor in percentage and 2.4 in percentage. So we'll take that to the other part and just add 2.1 and 0.24. Now if we print this, it should be a much better fit in ASA. So we are able to scale these parts and get them somewhat correct. We'll print it out and give it a try to make sure it worked. But we're just kind of guessing here. We're taking some measurements, trying to make an educated guess on how that part shrank. And remember, I just told you a little while ago, it's going to be different for every part. But there is one thing that Prusa Slicer now has in the 2.8 release that can help you track the changes based on the filament you use. Because theoretically, if there are a percentage of changes like we just saw in this part, it should be the same for everything you print out of that filament. Now, again, it's going to change based on what you print, but at least it's a good starting point, and you can save that for future models that you print out of said filament. So this is Prusa ASA. So I'm seeing it shrink a bit. I have 100.21 as a percentage for X and 100.24 as a percentage for Y. What you can now do is go into Filaments, find that filament that you've been printing, go to Advance, and you have Shrinkage Compensation. All it's doing is scaling, doing the same thing that we just did, but now you can save it in your filament preset, so that when you go to print it next time, you'll already have that compensation. And I'm going to try this out for myself. As I go through different projects printing ASA, I'll see if this compensation is enough to keep it closer to the PLA specs that we've been using. Now, they do have X and Y as all 1%, which is probably a good thing to keep those both consistent. You saw again we had 21 and 24. Let's just call it 22. So here, we don't even have a percent difference. We're just going to do 0.22. And again, Z for this project, I didn't care, so I didn't measure it, but you can also change that up as well. But now you can save this. We'll just call it 0.22 compensation. And now I can use that to try to combat any shrinkage from when I'm printing Prusa Mint ASA. And here's the before and after we adjusted that shrinkage compensation X and Y, that 0.22 setting. So before, you could see that clip. We'll go to the other side. You can kind of see the bow there because the clip is really tight. And then after, it's a lot flatter. And you can kind of tell here on the gap where the clasp is. You can take a look at this one, and then we'll flip it to take a look at the other one. These are much tighter. Just overall, after that compensation, it's a lot better fit. So I realized this video was just a bit all over the place. We talked about measuring prints, filament types, CAD, but I'm trying to give you an idea of the things that I go through in my projects to try to compensate for some of the nuances in 3D printing. If somebody says they have a part in PETG, for example, and they want to reprint that in ASA, because if they needed a little higher temp tolerance, they'd have it. Well, it might not be that simple. Some of the holes might be too tight. It might not fit at all. And you need to know how to compensate for that kind of thing as you move into the different filaments when you need them to be just a little bit more versatile, especially when it comes to temperature. So hopefully there was something in here that gave you an idea of how to do something a little bit differently or how to do it at all, just to help you in your 3D printing journey. So that is it for today. I'll see you really soon on the next one.